Hi, thanks for being here. I'm Tom. I was a PDOT in the fall. I have been working with Yang-Fei Zhang to simulate super-Eddington accretions of dusty gas around black holes. Why this is important? To give you the context, there are two types of eddy galaxies, C-phase 1 and C-phase 2. C-phase 1 usually have the broad emission lines, which indicates they are high-velocity gas near the supermassive black hole in the galactic centers. They all have the strong continuum emissions, which means that the C-phase 1 have the direct field on the eddy galactic nuclei. In contrast, C-phase 2 have only narrow emissions lines, and they have weak continuum emissions. This is because the C-phase 2 are the off-axis galaxies. We have the high filling angle to the AGNs, so the AGN emissions is obstructed by the equatorial dust molecular torus. We have observed several extremely active galaxies. Narrow line C-phase 1 is one of the examples. They have all the properties of C-phase 1, but they only show narrow lines. They have very blue optical continuum and shows iron 2 emissions, and they are extremely bright. That their accretion rates can be super-Eddington. Since the supermassive black hole the supermassive black hole are actively accreting, and they tend to have the lowest black hole mass. This source is the brightest narrow line C-phase 1 we have observed. They have the supermassive black hole of 10 to the 7 solar mass, and the accretion rates can be 20 times the Eddington accretion rate. We have also observed the ultra-fast also that has the speed more than 0.1 times speed of light, launched from the narrow line C-phase 1 galaxies. Quasars are the other examples of the super-Eddington systems. They are the high redshift, which has the redshift parameter more than 6, and they are hosting a supermassive black hole, which the mass is more than 10 to the 8 solar mass. This plot shows you the mass of the quasars as a function of the redshift parameters. And these two lines show you the growth path of the black holes which is founded by the first population 3 stars in the very early universe of the 10 solar mass and 100 solar mass, and assuming that they keep accreting at Eddington accretion rates. You can see that there are some quasars, they are too massive and they are too early. That they need to have the super-Eddington accretion rate at some phases. And since those supermassive quasars need to have a continuous, sustainable super-Eddington gas supplies from the galactic scale in the short time to go to be very massive. So some quasars need a super-Eddington accretion rate to grow. It is impossible to analytically analyze the super-Eddington disk because it involves a lot of complex physical process, but we can simulate it. Over the last few decades, there have been a lot of simulations on the super-Eddington accretion disk carried out using the novel radiation hydrodynamic simulations. In 2005, Ken Otsuka has carried out the first simulations on the super-Eddington disk, and he has successfully revealed the structure of the super-Eddington disk. He found that optically thick gas traps most of the radiations, and then it produces a large radiation pressure around the equators, and it puffs up the disk gas to form a geometrically thick disk. And it also launched a wind in the polar axis. Later, in 2014, Yang-Fei Zhang has run the first radiation magnetohydrodynamic simulations on the super-Eddington disk using his finite volume radiation transport scheme, and he found that the super-Eddington disk can launch a very powerful wind. And then later, Sadowski and McKinney has incorporated the GR effect in the simulations and run the 3D simulations, and they found that the super-Eddington disk can even launch a even higher velocity wind and launch a relativistic jet from the spinning black holes. Those simulations show the great opacity radiation transport scheme. However, all those simulations are the small scales which focus on the disk close to the black holes. We are still missing the flow structure in the large scale. We don't have any large scale simulations on the large scale super-Eddington flow structure. In the large scale, the gas becomes much cooler at a large distance. The source view are surrounded by the opaque shells of the molecules and dust. We don't know whether those dusty molecular gas can suppress the Eddington accretions, or those opaque gas may attract the super-Eddington emission. Well, we are still missing the large-scale accretion model. There is a simplest accretion model, it's called bonding model. It assumes the gas is spherically symmetric, and it uses a Newtonian description to describe that the gas accretes toward the central compact object. When the gas passes through the bonding radius, it becomes supersonic, and the negative gravitational energy becomes greater than the outgoing thermal energy. When the gas opposed to the central compact object, this becomes free flow. In the recent decades, there have been simulations found that when we inject the angular momentum in the gas, a torus disk structure can form in any conditions. This is one way we can find out the large-scale flow structure. However, we still don't understand the effect of the angular momentum on the luminous super-Eddington gas. So we are leaving all these three big questions. What are the large-scale structure of the inflow and outflow in the super-Eddington systems? What does gas do to the radiation and its surroundings? This is related to the AGN feedback problem. How did supermassive black holes sustain super-Eddington accretions? This is related to the AGN evolution problem. To attack these problems, I use Athena Plus to carry out the simulations. The Athena Plus solved the hydrodynamic simulations and incorporating with the radiation transport equations. In Athena Plus, it used the radiation transport scheme developed by Yang-Fei Zhang, who has used the finite volume approach to solve the full radiative transport equations for the more accurate treatment of the radiation in optically thin regions. Later, Yang-Fei Zhang has also developed a better method to iteratively, implicitly solve the radiation transport equations to reduce the time step and reduce the time scale separations between the hydrodynamics and radiations to speed up the simulations and for the more accurate radiation treatment. Well, we need to know the scattering and absorption opacity to solve the source terms. In the past, we usually assume the gray opacities. In my project, the gray opacity is good enough for the high temperature gas, but it is not accurate in the low temperature. Therefore, in my project, I use an opacity table that is integrated by Su in 2021. It has included the atomic opacity, molecular opacity, and dust opacity. They have integrated the nano atomic opacity table and which is dominated as a high temperature, more than 5,000 K. Molecular opacity table provided by Friedman. This is important in the moderate temperature from a few hundred to a few thousand K. And the dust opacity, which has calculated the contributions from the water ice, the astronomical silicate, the triolite, and the refractory organics, and also considering 4 different gram sizes. We assume that the dust moves with the gas, and the dust opacity dominates at a low temperature below the sublimation temperature. These 2 plots shows you the opacity, the Wolfram mean absorption opacity, and the Plum mean absorption opacity. The y-axis is the gas density, and the x-axis is the temperature. The dust opacity, molecular opacity, and atomic opacity dominate as 3 different temperature regimes. And from the color, whether the color higher the opacity, you can see that the dust opacity can be comparable to the atomic opacity. So the dust opacity is important. In my simulations, I initialize from the Bondi solutions and then set a super-Eddington Bondi weight and set a black hole mass to be 10 to the 6 solar mass. And in future, I will also simulate other black hole mass. My simulation domain cross the Bondi radius and also import the opacity table. I have first carried out 1D test Bondi simulations for different accretion rates, 5 different accretion rates. We evolve the adiabatic Bondi solutions to the radiative Bondi solutions in the steady state. Here, the left panel is showing you the gas density. The middle panel shows you the inflow speed, and the right panel shows you the mass accretion rate radial profiles. In the steady state, we found the gas density and the inflow speed increase from the adiabatic solutions. The mass accretion rate has been increased by a few 10 times from the adiabatic hydro-only solutions. We have also found that the gas temperature, which is shown in the left panel, has dropped by 2 to 10 times. So the gas temperature has dropped, but the mass accretion rate has increased. We found the entire accretion flows become supersonic, and the sonic points has moved out beyond our simulation domains, and the entire accretion flow profiles becomes more free-flow-like. While we have also checked the radiative luminosity of the radiative Bondi solutions, and we found they are all sub-Eddington, and the radiative efficiency is only 10 to the minus 5%. This is because for the 1D accretion flows, the only energy dissipation mechanism is only compression. In reality, the gas should be rotating, and the rotations can drive the turbulence, which can help to dissipate the energy into the thermal and the radiation energy. Therefore, we need a more realistic conditions. I'm carrying out the 2D simulations on the rotating Bondi-like accretion flows, where I inject the angular momentum in the gas beyond the Bondi radius. And this angular momentum has the viewing angle dependency, where I use the Gaussian in angle distributions with the height to radius ratios of 0.5, which is a typical thick towards this thickness. And the angular momentum is decided by the ambient gas-specific angular momentum, which is characteristic by the circularization radius, where the gas, when the gas flows at this radius, it will circular around the black hole as a circular orbit. I also assume that the flow has the viscosity using the alpha prescription with the alpha equals to 0.01. and assume that the viscosity, the physiosphere is MRI sample. So I only keep the alpha and the theta phi components in the viscosity. Since the bonding scale is much larger than the light times light quotient scale, it is very difficult to simulate the radiative bonding rotating accretion flow from the beginning. My strategy is that we first simulate the hydrodynamics to first obtain the rough structure of the large-scale accretion disk first, and then we resume the simulations with the radiation hydrodynamics. We have done the hydrodynamic simulations with different angular momentum. Since I have several numerical and computational issues, we haven't done the radiation hydrodynamic simulations yet. But let me show you the hydros only one. In this one, the RC is equals to 0.1 bonding radius, and the alpha is 0.01. You can see we start from the bonding spherical symmetric bonding profile, but since the gas around the equator has a lot of angular momentum, it's formed a disk around the black holes. While the ring is launched from the disk and flows along the polar axis and creates the funnel along the torus axis. This plot shows the time evolution of the accretion rates. Overall, we found that the accretion is strongly suppressed. And the right tooth panel is showing you the radial profile of the gas density and the rotational velocity along the equator. You can see it is forming subcaplarian disk, torus disk, and we found the density profile in the this density profile. The power law index doesn't agree with the A depth and the C depth models. A depth is a accretion-dominated accretion flow, and the C depth is the convection-dominated accretion flow models. But the index tends to be close to the A depth. We are still carrying out the 2D RHD simulations on the rotating bonding light flows simulations. Later, we hope to study the combined effects of the gas angular momentum, mass accretion rate, and radiation feedback. My intuition is that there are only two scenarios. Either it could be too strong feedback, that the radiation from the sources can have a too strong radiation pressure pushing out the dust gas, which not allow the super-Eddington accretions to happen. Or another scenario, the feedback is weak enough that can still allow the super-Eddington accretion to happen. Do I have time? But yesterday, I have just guessed this yesterday, that it seems that our models tend to favor the too strong feedback scenario, where we found that the radiation pressure tends to sweep away the gas from the inner region. Because the radiation force is too strong around the bonding radius. But I want to emphasize that we have just obtained these results yesterday, and this result is preliminary, and we are still checking the results. And then we hope to, we eventually will address the three big questions. And thank you.
Questions for Tom? I've got time for one. So I was curious about what is determining the gas temperatures in your simulation. Did you say that it was just adiabatic evolution?
Yes.
So would radiative cooling processes potentially also play a role, or is it just too inefficient?
Well, since we are using the radiative transport series that has been self-consistently include the radiative cooling, and our gas temperature is range from 10 to 5 Kelvin.
Okay, so you are modeling like the processes by which the gas is emitting radiation?
Yes, yes.
Okay, thanks. All right, any other questions? If not, let's thank Tom again and all the speakers in the session.